All right, so we had a long discussion about communication. I just want to wrap up the last part, which was the Berkeley sockets, how they look like. I'm just going to go through the diagram very, very fast. Right? And that's going to remind you what kind of operations you can do. So basically, you have two trajectories. You're either a server for that particular connection. You're basically either the initiator of the connection, which means you're the client, or you're on the other side, which means you're the server. Right? Essentially, if you're the server, you have to wait for something to happen and then respond. Once the connection goes, either party can serve as the initiator, whatever else needs to be done. But this is only about setting up the communication. Right? So from client's point of view, things happen in the following way. You have to know the IP address or the name, and you resolve it with DNS. We're going to talk about DNS later for the machine you're trying to connect to. Right? So you first create the socket, then do a connect. Connect requires you to say who are you connecting with, right? While you're doing the connect, magic is going to happen with TCP/IP, and an actual accept call of the server that must have been on this trajectory actually happens. Some handshaking goes on, and then you can go and do your writes and reads and writes and reads. The succession of writes and reads, it's not anymore guided by who's the server, who's the client. It's guided by whatever it is that they are trying to do, right? So for example, the client could make a connection, but then immediately try to read instead of write, because it's expecting the server to initiate the actual useful communication, right? So this is where the protocol, this is where the protocol that's implemented actually kicks in, right? This is why you have all of this read, write, read, write, read, write. At some point, there are closes. A close here will mean that there is a notification on the server to say the socket got closed and the other way around. Okay? So the TCP/IP protocol and all the infrastructure that the operating system provides, and something similar, it's happening except the idea of the connection with UDP, right? Provides you all of these goodies. So you're just calling these high-level functions. Literally, there is a high-level function in libc that says connect, write, read, and the read is going to provide a special, or the read or the write are going to provide a special value out to tell you, hey, the connection got closed, and then you have to call close yourself. As a server, let's see this very fast. So again, as a server, you create a socket, you bind it. Once you bind it, no other server on the machine can bind it. This is very important because if you run a program that binds to a port, any other program, including another copy of the same program, is going to fail when it tries to bind. Okay? So you bind. Then immediately you listen. The moment a connection is detected, there is a handover, and you can accept and continue to listen at the same time, right? So you can spawn up, for example, a thread that accepts, and the main thread, for example, would listen. This is essentially what Akka is going to do, and it's listening to a special port which probably can be configured in order to form those connections between the machines. Now, the way, for example, the actor communication in between machines is mapped, such pipelines, such connections between various engines are created. They are point-to-point, so it better be the case that any pair of machines has at least one such connection. And the framework is going to decide exactly how it encodes the message that goes on the wire. Right? That's essentially some form of serialize and deserialize. Since it's Scala, it can use its own format because the other end is going to understand it. If you want two different languages to talk, then you have to standardize the protocol. I mentioned this last time when I talked about Scala talking to C++, for example, or things of this sort. All right? Good. Any questions about this? Well, my advice is try not to be at this level. Try to use high-level libraries to get the job done. And essentially, the Java libraries that are out there, or even the Scala libraries, you have sockets. They're very high level, and they're going to hide most of this from you. Okay? Or even better, the framework itself. But you have to remember this kind of a picture when things go wrong, especially the bind. It's very, very dangerous. Right? Again, once you bind, you cannot, until you kill the process, which is going to result in an unbind, automatic unbind, you cannot bind to that port anymore. Okay? So a particularly troublesome thing to do, for example, would be you have, I mean, this would be an interesting exercise that could keep you busy for a long time, and most of you would probably not get it done, is to design a solution so that multiple processes can actually listen to the same port. It's very, very tricky because you have to essentially designate one of the processes to bind and then to do handover of sockets in between processes. Apache does that. Okay? So Apache can do some of this magical stuff and hand things over to PHP or whoever else is running in whatever context and have multiple processes running. But it's really, really tricky, right? You're much better off by creating a single large process, actors and whatnot, and keep things under control. I mean, it's a much nicer model. OK, let's switch gears and talk about something else. So we talked about connection-oriented communication. We talked about remote procedure calls, which are some sort of a high-level communication primitive. There are some other communication primitives, and actor model gets close to that. And one of them is message passing communication. So communicating by messages, right? So message passing interface, MPI, is essentially highly standardized protocol with very good implementations designed for the high-performance computing community. And those guys are mostly concerned about extremely efficient, bit compact, bandwidth compact communication. Okay? Now, but let's think a little bit about when it comes to messages, right? To a large extent, messages are simpler than the remote procedure call, and they are simpler than the communication itself. The connection-oriented communication. Right? In connection-oriented communication, essentially, you have to establish a connection and then do something like messages going around or something like streams or whatever it is that you're doing. And there are multiple ways to use such a socket, right? And then close it and all that kind of stuff. But when it comes to messages, in principle, all you need, so what, especially asynchronous messages. So let's think about asynchronous messages, by far the simplest one. So there is no automatic reply to anything. What's the core problem that I have to solve? Have a way to address who do you want to send a message to, and just the act of sending the message, right? And that's it. Now, for any kind of reply to come back, it's the problem of the other party to find its way back. And the way back would be fundamentally different. And actually, even the way forward, it doesn't necessarily need to be a straightforward one point-to-point connection. It can be going over all kinds of hops. Okay? So if you think about it, for example, email is some form of message passing. Right, with something else that we're going to mention in a second, persistence. If I want to send you an email, essentially I'm sending this message that you might have the feeling gets directly to you, but it virtually never does, and it's going to do a number of hops. It's transparent. It has its own way of moving around. Right? And by the way, each leg of the journey is going to be an actual full-fledged connection-oriented communication. Right? In order for whatever the message that it's in the email ends up in your inbox. That means what? Well, something you can look at later. We are going to talk about this in a principled way in few slides. Okay? But MPI essentially has these low-level primitives to allow you to establish such a communication. So first, you need to establish a communication between two machines. It supports other things, for example, broadcasts and multicasts, which I'm going to come back to because they are fundamental. And then essentially what you need is just a way to form the content of the message and to send it. Now, MPI, because those guys are truly paranoid about performance, has many variants on how the message is built and how the message is sent. Okay? And they really don't care which one you use, and it's your problem to use the one that's efficient and to know that's efficient. And to some extent, this is kind of the worst library because you have to be extremely sophisticated to use it, right? So just to give you an example, I'm not going to go through the whole list, but an example would be for receive, right? Receive a message but block, or receive a message but don't block, right? So that means pick to see if there is a message, not go and do something else and then, right? Now, for example, let's think about the actors in Scala. Which of these do they implement? They essentially, so it's actually conceivable that the actors in Scala can be implemented on top of MPI. The only thing to change would be the actual deep communication that happens in akka, literally. And for all we know, they might use MPI, and we don't even know it. Well, they don't, because we know that, I know that they don't ask you to install MPI libraries and whatnot. Okay? But they could. Right? Now, at an actor level, one of the nice things about the Scala, the akka actors, is they don't offer too many of these choices to DZ you up, right? So whenever you say receive message, then you're basically just blocked there and you receive any of the messages. MPI is not like that. It's simply too low level, okay? So inevitably, if you end up using MPI, you either do relatively simple things for the people that are trying to write very large simulators, right? Either write very simple simulations. They require large amount of processing power and so on, but they are fundamentally simple. Or you have to build something on top of it because it's too hard to deal with the full-fledged complexity of MPI. Okay? Including some sort of an actor model. That might be actually a faster way to get stuff done. Okay? So I'm going to let you have the fun with reading the MPI interface, but it's essentially some way of sending, some way of saying I receive, and some way to pack the messages. Okay? Especially the packing of the messages interface is really low level and really annoying. Right? In Scala, for example, you can say, you see this complex message, just send it. Right? Were you ever worried about how exactly the message is sent and what's happening on the wire? No, because you put it here and it pops up in the other place. That's not the case in MPI. You literally have to take whatever that you want to send, chop it into pieces that are integers, doubles, floats, and whatever basic data types they support. And at the other end, to reconstruct it. So you have to provide a deconstruction algorithm and a reconstruction algorithm, a serialization and a deserialization with the MPI interface. Right? You would literally have to walk through your object and say, oh, this is an integer, so let's fire up the integer writing. You remember the stubs that we discussed in the context of remote procedure calls. Essentially, in MPI, you have to write the equivalent of a stub by hand. Now, there are some tools that might generate MPI stubs for your data structure, but they're not in broad use. So most people will just go and bite the bullet and write that low-level stuff. The low-level stuff is very dangerous, okay? Because any mistake in there, it's hard to track, okay? So something that happens all the time, and I want you to remember this. The lower level you go, the better your opportunity to mess with it and improve the performance, but the more spectacular the failures, right? It's much harder to ensure correctness the lowest you go, because there's nothing between you and those bits, right? There is no mechanism. So for example, you can say, I'm not going to include type information in the bean packing. By the way, MPA doesn't put any type information. I'm not going to put any type information in the package because that saves me bits. That's great. But if you made any mistake, you won't even know. It comes scrambled at the other end. You won't even know how is it and what it is. And especially transient errors. Sometimes you make an error, sometimes you don't make an error. Extremely hard to track, right? Languages like Scala take a very defensive approach in which they say, we're going to sacrifice a little bit of performance, but ensure essentially debuggability, right? So Scala, when it actually serializing those messages, is going to put a large amount of information, so it knows on the other end if the correct kind of message pops up or doesn't pop up, right? So it's going to do all of that for you. But I want you to understand that you do lose a little bit of performance, which might not matter at all for small messages, right? So when it comes to optimization, and this is maybe something very important to mention, right, because I see it happening all the time. When it comes to optimization, you have to teach yourself to optimize only when you should optimize. Okay, the biggest mistake is to directly think about the optimal algorithm and to implement the optimal algorithm and never to even consider the simpler algorithms. Because your code, it's already complicated in your head. It's going to be complicated on the computer program, and it's going to be very, very hard to debug later, right? It's probably much better to use some high-level facilities and then to try to evaluate if they do the work well enough and not to replace some components, rather than just thinking this super complicated optimization on way, right? You have to learn restraint. It's not so important in this class, but it's crucial when it comes to, for example, things like database implementation, where the more you optimize, the more spectacular you fail, essentially. And your code is not even faster. That's the problem, okay? All right, now, when it comes to, so MPI, extremely important for high-performance computing, I would say. High-level interfaces, much better. Now, when it comes to messages, you can actually raise the stakes a little bit when it comes to message delivery, right? For everything we talked so far, the idea was that the sender and the receiver are there, at least in terms of running at the same time. They don't have to be physically at the same time. I mean, somebody has to be physically there at the same time. So think about two actors on the same machine. How do they communicate? Well, they don't have to be there at the same time, right? Because the message gets copied in a message queue, but it's in memory. And then later, the message, whose message queue we put something in when we send the message, is going to look in the message queue and say, ah. It could have been the case that the actor that is watching that specific message queue had nothing better to do and was blocked on the message queue, in which case it gets unblocked fairly quickly, let's say. Okay? But in that circumstance, they had to live in the same memory space, and they were communicating through a memory region, in fact. Now, that memory region is actually thread safe, and it's in fact some sort of a queue. Okay? Good. Now, what about the remote actors? Now, when we talk about remote actors, let's draw a picture. Just remember that all of these things are virtual. In the end, it's only bits and instructions that run. I mean, all of this is kind of a pretend game that allows you to organize what is it that, I mean, how to reason about it. It's not so much what precisely it happens, but how to reason about it, how to think about it. Right? So when it comes to actors running on two machines, right, so this is the first machine, second machine, I'm going to have some sort of a TCP/IP connection established here. If it's not established, the first attempt to communicate with an actor on the other side will establish the communication. This is what Akka does for you. Again, an interesting project in C++ is to implement all of that and deal with all the errors and all the things and whatnot. Okay, so this is our TCP connection, TCP/IP. Okay. Now, when I'm saying that this actor here, actor 1, talks to actor 2, what exactly does that mean? If they would be on the same machine, it would copy in a message queue, and actor 2 later will look at the message queue, right? Now, that could still happen, but certain things have to be on all the time, because otherwise the communication doesn't happen, okay? To some extent, okay? So this actor 1 somehow has to get the message on the wire, and somebody has to listen on the wire and delegate it to actor 2. So there is this handover thing, right? Probably what's going to happen is actor 1 talks to some kind of a super actor on this machine that's only responsible for putting things on certain wires, and that's provided by the framework. You don't even know if it exists. To you, it's API. You say, send message. But in fact, what's happening even in Akka, when you're establishing a remote connection, when you say, I would like to talk to this remote actor, what's in fact happening is there is an A2 prime that looks like a real actor on your machine. And you're really just talking to A2 prime. That's some sort of a proxy actor. Okay? So instead of really doing this squiggly line, you're really talking directly to this A2 prime. This A2 prime looks like an actor to you, but its only role is to do whatever it takes to put information on the wire. Now, of course, you need a proxy on the other end, right? That's going to look like an A1 prime. That's going to talk to A2, to the real A2. So for remote communication, you have to double up on the number of actors because you need these proxies. And these proxies are special because they will not communicate through the normal messages on the other part. They communicate through this special TCP/IP connection. Okay? But once the message is delivered on this side, in whatever way to A1, it can be broadcast, it can be sent to A2. These guys have to be on essentially all the time. So there is that they meet in time, kind of. So somebody listens at the end of that connection. Now, you can raise the stakes even more when you think about messaging systems that allow you to come back much later to retrieve the messages, even if the program went up and down, right? So some sort of persistency. Okay? Now, you might ask the question as, hey, why would I do that? Right? Because if I want to do some computation, like you've done in the first project, then I'm going to fire up all the guys, and then the messages go around, and then we shut down everything, and we're done. Well, you could use messaging, for example, to replace some of the facilities offered by email, which has its own big problems and so on, or alternatives to email, right? Now, for something like that, you don't want to be worried about what machines are up and what machines are down. So somebody has to store those messages, really store them, until potentially much later somebody comes and picks them up. Right? And this is what the enterprise messaging systems are all about. Right? So instead of thinking about you have a bunch of these actors that talk and so on, imagine that you have, I don't know, something like 100,000 employees that use tools to communicate. And you need a system that allows all of those messages to go around, and you need to provide persistency because they keep on, I mean, they use cell phones, and they use laptops, and they use desktops, and servers, and whatnot, right? and you're not allowed to ever use lose any of those messages, and you have to deliver them. Now, that's a completely different kind of problem that actually needs to be solved, right? So if sender running, receiver running in terms of machines, TCP connection, and you deliver it, wash your hands of it, right? But if the sender is running and the receiver is passive, right, might even be woken up much later as a process by something, right? So, right? Now, when it comes to the API, you always have, especially when it comes to messages, you don't need much. Now, you could do the fancy stuff, for example, that MPI is doing. But the simpler, the better. And too many options can kill you as fast as no options, right? So I would say MPI people went way overboard. Now, I understand it as a framework building library, but it's virtually impossible to use in any sophisticated scenario by hand, okay? So when it comes to generic message queuing models, I might stick only with put, get, right? Append a message to a specific queue. So you have a notion of queues and messages, right? Now, in the normal actor model, each actor had a queue. And essentially sending a message to an actor meant put a message in its queue. And then somehow the actor watches the queue and wakes up when there is something in the queue. Not our problem, is the framework designers dealt with that. But you can actually relax this for really large messaging systems, enterprise-level messaging systems, in which not only multiple not necessarily actors, but multiple parties can put a message in a queue, but multiple parties can take messages from the queue. For example, that's convenient to do some sort of a round-robin resolution of issues. For example, you can use this for a ticketing system, right? So you have tickets coming in, they get into some kind of a message queue, and then various employees can pick tickets out of the queue in whatever order, right? So it's not necessarily, you don't have a tie-up between entities like actors and message queues. You could relax them, okay? So put a message in a specified message queue, right? You still have the problem of how do you connect the name with where physically that message queue is, whatever that means. Get, it's the opposite, right? Get a message, block until a message is available in the message queue. Might or might not support things like a specific variant of the message or not, right? Poll is basically, is there anything in there? So that you don't block, right? And notify, now this is getting interesting with the notify, okay? So here is basically the situation, especially in very, very large systems. It's very annoying to block one of the processes to keep on watching the pool. Now, with the actor model, you can kind of do this, right? Because you can designate an actor to be responsible by just watching one resource, right? And you basically say, hey, you're responsible for listening to messages from the big boss, and when one shows up, you tell everybody else in whatever way. But you're the only one that watches, okay? But if you design software, and these messages are put together so they can be used from a huge variety of operating systems, languages, and whatnot, right? Then in some of those languages, it's very inconvenient to do things that you can actually do with actors, to dedicate a thread only for that purpose, right? And actually, even in the actor model, it could be very tricky. If you're watching, for example, 10,000 such queues, you're in deep trouble, right? For that reason, I mean, the pool can essentially say, every now and then you say, do I have anything to have? It's like checking your mail, right? Either your email or, even better, your physical mail. It's, did you see the postman going by? No, maybe yes, maybe no, let's go and open the, annoying, right? This notify is designed to remedy this, and it's some sort of a callback. How many people here know what a callback function is? Okay, good. So what's a callback function?
JavaScript, they use these special functions called callback functions.
No JavaScript. What's a callback in general? So unfortunately, let me say why I'm saying this. Just 1 second. I'm saying this because if you learn a concept in the context of a language, it gets twisted in the wrong way. These are fundamental concepts. And the notion of callback is fundamental. JavaScript just uses it for everything, and we can even discuss why, right? So what's a callback dissociated from a language?
It's a procedure that's to be called when a certain event occurs.
Right. So callback is essentially a function that gets called by the system when, for example, a message got placed in a box. Now you have many problems with such functions, right? And JavaScript, actually, this is the reason JavaScript doesn't have functions, it has closures. What's the difference between a closure and a function?
A closure has the environment context.
Right. So let me translate for everybody else. So here's the problem with the function. What would the function do? You see, normally when you call a function, you have the outside program, calls the function produces a result, and you got the result, right? But now this callback function really is not a function. It's more like some sort of a procedure that's supposed to change somehow the state of whoever it needs to change the state of to produce the consequence of firing up the callback. But normal functions really have no way to access the context of anybody, right? So if you think about, so I want you to understand this because this is a fundamental problem with any callback in any language. You have to solve this to use callbacks. This is the stack, right? Now, for example, in C, this is the way it will work, right? Up to this point in the stack, it's used by a particular program. When you call a function, you dedicate another portion here of the stack for the callback function. But not for the callback function, for the function when you call a normal function. But when C is running, it's really not crossing this boundary. So C as a language doesn't like to go back and look at what else was on the stack or in any other part of the program. Now, you could essentially, because you allocated something on the heap, you could, in the function call, pass by reference some objects, and then it knows about it, right? But C functions don't go and look on the stack who else is there, okay? So the execution context of a function normally is what's on the stack, only in the portion for the function, plus global variables, okay? Plus whatever it's in the heap, right? But if I have a callback, then the callback, eventually is going to be put on some sort of a stack or something, right? First of all, it's not clear where is it running. It might run actually on the server, or whoever is hosting the message queue, right? So in those circumstances, you have a big problem. You might not even be in the same memory space as the program that's supposed to process that message, right? So it becomes very problematic. So what the closures do is they, in fact, have some sort of a pointer to a context, a set of variables that it has access to, right? That don't necessarily even live on this stack, could live in other stacks, right? That's really what closures are. And some of the high-level languages offer closures, and Scala has closures, right? So you know you use a closure if you have this, right? Something like var I, it's equal to 0, and then you say function, blah, 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 and you refer I here, right? The I here is the I outside the function. So in fact, this is not a function, this is a closure, because not only has its own local variables, has access to the context in which it was defined. You can take this function, manipulate it like a normal object, give it to somebody else, and when they call it, they still have access to I, this I, right? So that's really a closure. C doesn't have closures, right? Because and this is why C doesn't look in the stack and doesn't allow you to manipulate the stack. And right, you can do that only in assembly if you trick it. You can't just backpedal on the stack. Well, you can cheat. But even then, you would have access only to specific things. So implementing closures is a much trickier business than implementing normal functions because of all this context that you have to keep around, right? So when we say callbacks, notify means it calls a function. You have to be worried about of what context will that callback have, right? So still the problem is not completely solved, and you might still need to hop over various things. Yes?
How to identify these variables that he can access?
You mean how it's doing it?
Yes. For example, in GWT, when we were working with callbacks, we were defining final variables to be able to...
Now, one second. GWT is written in Java, translates into some weird JavaScript, and it's the worst example to talk about what closures do because it's whatever the Google people that designed GWT did, and I don't like GWT, so I never bothered to look at what it does. We tried it, and it's not good, right? I mean, it's just too complicated. So I don't know what's happening in GWT, but essentially any language that has closures has to solve these problems. Right? Some languages, for example, can manipulate explicitly these environments, these contexts. Right? For example, R, statistical language. You can send as parameters these environments, and you can carry them around, and then you get the closure-like behavior in which you even know what your environment is, and environments can link to other environments, so some kind of chaining. Right? But something is needed when you implement notify. So notify could be very tricky. To put things in a queue and to take things out of the queue, not so bad. To be stuck on a queue, potentially not so bad because you have facilities in the operating system. Right? How many people here took an undergrad operating systems class? Hopefully all of you, right? Good. So let's even think about the basic stuff. And then I'll spend a little bit of time talking about gossip. Actually, the new project you have asks you to implement a protocol. The protocol is fully defined in the description of the project. Make some references to, as we discussed in class. We're going to discuss that in class. But in principle, you have the entire protocol in the project. Right? So you can start implementing it right now, even if I don't complete the discussion about gossip, which I might have to wrap up only on Tuesday. Right? I will mention the high level, what gossip is. I'll make sure that I do that before the class ends. But let's think about something very basic, which is you are implementing the message queues for same machine actors. Right? What exactly does that mean? You need to get that message queue going. Right? You need to implement some data structure called the message queue. Now, sending, well, it depends on what message queue you implement, whether it's bounded or unbounded. But let's do the easy thing first, which is unbounded message queue, which means you have a deep disrespect for it is the queue getting too large and you keep on putting things in the queue. So adding things to the queue are easy, right? So we have a basic mechanism which is crucial when you do inter-thread communication. Mutual exclusion, right? So what's mutual exclusion region? Right? You basically can signal is begin mutual exclusion, do some work and mutual exclusion, and you're guaranteed, and it's the problem of the low-level part of the combination operating system and hardware and whatnot, that no other thread can enter the mutual exclusion region once one thread is in, right? So when you'd say lock and then unlock, and this is parameterized by a resource, right? So I have the resource R. Lock R, unlock R. This essentially is some sort of a variable that's somewhere in memory. If I say lock R, the moment I actually got the lock and I can proceed, I'm guaranteed that nobody else that says lock R can succeed until I unlock R, in which case the other guys could be unblocked. Okay? So that's great, because that will guarantee that I can manipulate here things that could disrupt other threads. So this is a minimum of the minimum to use. Okay? So when it comes to a message queue, that might actually be enough to put messages in the queue, because all I want to do is lock the queue. So you have one of these mutexes or whatever it is for the entire queue. You say, lock the mutex of the queue. If I succeed, start essentially manipulating the data structure that keeps the queue, whatever you want to implement there. You can have a linked list and add at the end or whatever it is that you're doing. Put the element in the linked list, then unlock the queue. Done. I put the message in the queue. Right? But now the question is, how do you implement read from the queue? Now, if there is a message in the queue, the read is easy. Lock, take the message from the queue, right? And then unlock. But what if there is no message in the queue? So what are you supposed to do on a message queue if there is no message in the queue? To block and to wait until there is a message in the queue. Now, how do you implement the wait? Now, this is where you can produce truly disastrous solutions. Okay? The worst of the worst would be a for loop that looks like this. Forever, lock, check, nobody there, unlock, go back, busy waiting, right? Those are essentially mini infinite loops, right? They will use the full processor. Your CPU utilization is going to go to 100% even though you do no work, right? Because all you're doing is, it's me waiting for mail. Walk all the time to the box, open it, close it, open it, close it, go, right? Crazy. Not good. So you already see that things get subtle, so you need some sort of a mechanism to say, you know what, I want to go to sleep, so I don't use resources, but somebody has to wake me up when something interesting happened. And that's where we use what? So dig back into your knowledge about undergrad operating systems and give me the the name of the magic thing that can be used to, in fact, block here. I'm sorry? No, you can go to sleep, but the question is, how do you wake up when something is, right? It's easy to go to sleep, but then how do you know that something is there?
A signal?
That would be disastrous because they are way too slow. Yes? Too low level and too crazy. Interrupts on what? What am I going to do? Wake up on clock or what? So what I want you to understand is, quite often you need extremely low level, deep help to do certain things. The specific one here is conditional variables, right? So basically, you need the following mechanism. You need to be able to pair up a lock with one of these conditional variables. And essentially, this is what's going to happen. You have to be allowed to check if a certain condition is true. If it's not true, well, while you check, you must have the lock. But if the condition is not true, the lock is released, and you go into a special queue for this resource R. That's the set of threads that wait. And whenever somebody does something to this code, so there is a chance that the conditional variable becomes true, you can basically do a broadcast on the conditional variable and wake up all those guys. They start acquiring locks, just 1 second, in order to see if the condition was true. So what that mechanism will allow you to do is essentially allow one or more such threads to go to sleep until there is a chance that the condition might be true. Now, it's not going to be true for all of them because only one of them is going to grab the resource, but at least they don't stay alive and keep on checking in an infinite loop, right? Because look what's happening. Until somebody comes and puts a message in, there is no point in trying to look if there is a message, right? Now, if multiple threads were waiting, and you could have message queues on which multiple threads are waiting, then obviously only one of them is going to get the resource, and all the other guys will end up looking and not finding anything, right? So these mechanisms are extremely low level and are at the level of those threads, stopping threads, putting threads in a queue, waking up threads, right? Why am I telling you this? Because even if you want to implement these message queues, don't try to do it yourself with loops and things. Right? This is where pthreads or whatever libraries that implement these things come into play. You have no reason to go at a lower level than pthreads unless you're implementing an operating system. Right? So what's happening is things are stacked, right? Extremely high level things use lower and lower and lower and lower level, right? At the very bottom, there is some sort of hardware which itself can be virtualized. The art of surviving as a programmer is to know where to stop. You can always go all the way to the bottom and then spend a year and not getting good code running, when you could have written something in 5 minutes at the very top, right? And pretty much gotten the same performance. So Scala and the akka does you, I mean, first of all, it's not even Scala, because Java will do this. How? Well, yes. Java has a monitor implementation, which is a very fancy abstraction that uses these facilities, right? So in fact, Scala doesn't even do the work. It just uses Java libraries. How does Java do it? Well, it's in the Java virtual machine, right? Which is written in C, right? So let me tell you a secret. Everything is written in C, except the occasional stuff is written in assembly. It just comes down to C. It's just funnels to C, right? That means something, which turns out to be important, and I'll tell you the gossip. That means that absolutely all the languages have a connection to C and can call C. The reason is they are implemented at the lowest level in C, and one of the basic problems that had to be solved in any of these higher level languages is how to get work done, so they had to establish a nice way to call C, right? So what's Scala's way to call C? Well, ask Java to call C, right? And Scala just asks Java everything that means library. What's the Java's way to call C? JNI, right? That's that very, very low level interface. How does that work? Story for another time. I'll explain, because you can actually do that. This is the strange thing. Whatever Java people do, you can do it in your own C code if you have to, right? So my advice is stick to high-level tools until you run into a very tricky problem, in which case you have to understand how they do their magic to reproduce the magic with slight variation or complete variation. Good. 10 minutes, let's talk about a different kind of communication. So message queues, I might have next time some discussion about how the enterprise message queues look like. Let's talk about something different, and let me pose very fast two kinds of, one overall activity that you need to do and show you the gossip solution for that. I'll mention a non-gossip solution and then the gossip solution. So the problem is multicast. Right? Remember the broadcast we talked about? When you have a physical medium, you can just shout to everybody. You're essentially, when you have a common medium, shouting to everybody anyway. You might as well put some bits in there to say everybody should listen, not only this particular guy should listen, right? Wireless access works like this. But even Ethernet now, because of the switches, really doesn't like this kind of broadcasting. And actually, broadcasting requires special privileges even from the OS to send the broadcast message. So for the most part, you have point-to-point communication. But that brings the following question, which is, if I have a number of entities involved, how can a message from one internal or external participant go to everybody in a group, right? So it's some sort of a group communication. We are going to come back to this later, right? So a broadcast means send the message to everybody, right? And a multicast, it's essentially the same thing, but everybody is only some sort of an everybody in a list, right? So there is only a very subtle difference between, I mean, a broadcast will mean the whole world, which cannot be done beyond very simple networks. But multicast is, oh, I have, for example, a list of 100,000 people, and I want all of them to know that something happened. Okay. So the core issue is multicast. Right? Now, how can you implement multicast just using point-to-point connections, let's say? Yeah, you can use TCP/IP only, and I want to spread the message. That essentially means I can talk to, you see, I'm actually broadcasting now, right? I'm talking and you all listen. That's broadcast, at least for participants in this class. But suppose I can only talk to one of you at a time. How could I get the message around?
You tell me, I tell him.
Right, so, well, yeah. So essentially what we can say is, I contact a smaller number of people, and you contact a small number of people, and you contact a small number of people. Hopefully, things do propagate quite fast, and they go quite fast, right? So schools, before they had this fancy phone system in which they automatically call all the parents, right? They had this call trees. They made a convention that every parent knew the phone numbers of, let's say, 3 other parents, and when they got the message, it was supposed to call these 3 other people to send the message, right? So one way to get every participant to find out about something is, again, to form such a call tree. This guy initiates the message, so we'll send it to 3 guys. These 3 guys are going to send each of them potentially to 3 guys, and so on and so on and so on. Okay? So in this way, you could, if in fact, have a message that starts in one point and it's propagated everywhere. This is essentially a form of multicast. You're just spreading the word, the message around. Okay. Now, this starts to be an interesting research topic, and was researched over and over and over again. How can you do this efficiently, right? For example, the first guy could in fact call absolutely all the guys independently and just tell them message, 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 right? If you do so, what's the problem? It takes too long, right? If transmitting every message takes, I don't know, 10 milliseconds, and if you have 1 million guys to send messages to, then you can add up things and it takes a couple of hours, right? But if everybody sends only 10 messages and somehow they know what the tree looks like and they don't overlap, then essentially the time it takes is only the depth of the tree. It's the difference between a list and a tree. A list with 1 million nodes will take much longer to go from one end to another than a tree with 1 million nodes, if it's nicely balanced, even if it's binary. Actually, if it's more than binary, right, that the depth of the tree is logarithm-based, whatever the fan-out for the tree is. Okay? So things can get much, much more efficient. But you still need to form some sort of a tree. So the question is, how do you form the tree? Now, that's where a completely different idea comes into play, this gossip idea. Okay? Now, this idea might sound to you very, very strange, because instead of having an organized way to send a message to everybody, you can have a disorganized way, but prove theoretically that with extremely high probability it's going to work out. Right? So here's what you do. You pick, in every round, and you can prove that it takes about logarithmic number of rounds for certain networks. In every round, you can send the message randomly to one guy. Now, once any participant got the message, is going to do the same thing. Just at every step, randomly pick another guy and send the message to, right? So then, if the network looks like this, in the first round, this guy sends this message. In the second round, this guy sends, let's say, this message, and this guy sends another message, right? So what's going to happen is exponentially some wave is going to form, and it's going to go all over the place and fill in the space. And actually, these guys don't even have to remember who they send messages to and who they didn't send messages to, because you're guaranteed in a logarithmic space, if really you pick a guy at random, that you're going to spread the message around with very high probability, okay? So this is gossip dissemination. Now, in fact, the way you can think about this is to say that I have some kind of an overlay, a virtual network built on top of these nodes. And in this case, because I'm picking a random guy to send a message to, essentially I'm connected to, well, I have random neighbors, essentially. But you can experiment with different topologies here, and that's what I'm asking you to do in your project, to say a line, and then you can pick randomly a left or a right line, neighbor, or a grid with random connections, or a purely random connection, right? But in your project, I'm adding another interesting thing on top of it, which is instead of just doing a multicast, sending a message to everybody, you're going to carry out a computation. I'm going to come back to this later in the class. But essentially, this is, by the way, not that I need to brag about this, but in 2003, me, another grad student, I was grad student at Cornell then. Me, David Kempe, another grad student at Cornell, with my advisor, we wrote a paper in which we explained that algorithms for this gossip dissemination can be used for computation of first, a simple computation which is average, which you're going to do for your project. And then we explain how that can be generalized to an entire garden zoo of other things that can be done, as long as they have a certain mathematical structure, right? So your project, specifically, is going to be to experiment with various kind of networks to, in fact, compute average with a protocol that I indicate. The protocol itself is only 2 lines. Okay? Essentially, everybody maintains 2 numbers. And when they contact their neighbors, they're going to modify their numbers, and the neighbors modify their numbers in a certain way. And you have to make the whole beast converge and study how it does things and put lots and lots of nodes in it. And of course, you need to do all of this with actor models. Each of these guys is going to be an actor, and then all those actors have to talk according to various topologies and so on. All right? I'll come back with slightly more, well, I still have about 2 minutes, but I'm going to pick up a little bit the discussion next time, right? I'm not going to go into theoretical proofs why the algorithm converges, right? It turns out that a lot of average computation algorithms would converge if you really pick random nodes, but most of them would not converge if you don't have random nodes. And the one you're going to use is the one in the paper, in the 2003 paper. We wrote that converges always. Now, the speed of convergence could be very slow sometimes and sometimes very fast, and I want you to discover what's what, right? Now, you're going to build basically the following kind of skills with this project. One, it's actually implement a protocol. It looks simple, but it needs to be done, right? The second is write essentially a simulator with the actor model. And the third one is to be exposed to this kind of fancy things, to be able to evaluate yourself whether they are worth using or not worth using, and if they are worth using, when and how, okay? So what's happening is the world is full of these research papers of all kinds, and things look very cool, and you go in industry and say, hey, I Googled and there is this cool paper, let's implement it. 3 months later, you realize that it's a complete disaster when you deployed it on the real architecture, right? Writing a little simulator like this and trying it up and then fiddling with it in certain ways might allow you to, in fact, evaluate just how good it is, and does it fit your user scenario or not. I'm not saying that the research is fundamentally bad. I'm just saying it's not always on top of the kind of things you care about. And there's too much generalization sometimes claimed in some of those papers. Okay? All right, so that's your new task. And we still have to talk a little bit about communication. I'm going to have a quiz there on, I'm going to post it on Saturday. It's due Sunday midnight with whatever we talked in class. Right? All right.